This is Food Science 571, Food Process Engineering Technology. This is the instructor, Dr. Barrett Vaughn of the Department of Food and Nutritional Sciences. We are continuing with Topic 1, Problem Solving, and this is Lecture 3 of 4. This section of the chapter concerns mass and energy balances. And primarily we use mass and energy balances as an evaluation of individual pieces of equipment. Specifically with mass, you have the concept of conservation of mass, which is important in material flow, particularly liquid handling systems and dehydration, which you'll find later on in the course. But you have a general balance equation. The input, the amount of mass that goes into a system or a piece of equipment, minus the output, which is the amount of mass that comes out of the piece of equipment or the system, plus the generation, the material that's actually generated within the system, minus the consumption, the amount that's actually consumed or becomes destroyed within the system, is equal to the accumulation, which is the amount that actually stays in the system itself or the piece of equipment. Normally, with most of the things that we deal with, there is no generation or consumption. So the equation, the general balance equation, will then become input minus output equals accumulation. And usually under steady state conditions, which means that nothing is changing over time, that means that things aren't being accumulated over time, mass is not collecting within your piece of equipment or your system, no accumulation occurs. Therefore, the equation becomes input is equal to output. There are certain steps that we should use for mass balances calculations. First, we should collect all known data on mass and composition of all inlet and exit streams. Next, we should draw a block diagram or flowchart indicating the process with inlet and exit streams properly identified, and this includes the units of those streams, the complete units. Next, we'll write all available data on the block diagram, then we'll select a basis for calculations, mass or time. That would be either 100 kilograms, for example, or maybe per hour. Then we solve the material balances to determine the unknowns. Normally with these problems, there's a particular quantity, a particular stream that we don't have the amount for, and that's what we're solving the material balance for. This is the example that we'll use in this section. It reads as follows. A food leather is dried in a continuous flow dehydrator. The wet leather contains 0.80 kilograms of water per kilograms of leather, while the dry leather contains 0.20 kilograms of water per kilogram of dry leather. Heated, drying air flows opposite to the flow of the leather. Wet leather flows at 100 kilograms per hour, while dry leather flows at 25 kilograms per hour. What is the flow rate of drying air? This is a diagram of the example from the book, Example 2, as we just read. As you can see, set up is a rough diagram of the system itself, where you see the wet leather in the lower left-hand corner and the amount that's coming in, the dry leather as it's exiting in the lower right-hand corner, the dry air entering, which we don't know the amount of the dry air coming in from the upper right-hand corner, and the amount of water that's actually associated with that dry air. In upper left-hand corner, we have the dry air as it exits the dehydrator and the amount of water that's associated with that dry air. In the center of our diagram, we see how the water actually is transferring to the air, and that really gives an indication that less water is exiting with the leather, which is dry, which you would automatically assume. This kind of diagram will be helpful in setting up the problem itself so that you can go on to solve it. However, we're also including an alternate way of looking at this particular problem. This is the file diagram example 1 that shows a little bit more clear how this particular problem should be set up. This file should be available to you through Blackboard, and you may want to go ahead and print this off so that you can follow along. Here again we see the different steps for solving these problems. First, develop a flow chart for the system. I suggest you use either of the ones that were provided. Second, write a mass balance with no accumulation. Understand that solids going into is equal to the solids that are coming out of the system, and the water coming into the system is equivalent to the water going out of the system. Now the water comes in with the leather, goes out with the leather, but it also comes out with the air as well and goes in with the air. And you can write a separate mass balance for each component of the system. For example, the leather aspect and the air aspect. But be sure, and this cannot be overstated, take care of units using unit factors. Here from the book is the solution to this problem. This system has no accumulation. Thus, input must equal to output for all components: water, dry air, solids in the leather, and the sum of all these. The airflow must be sufficient to remove all the water evaporated from the leather. We begin by looking at the moisture and dry matter of the wet and dry leather. The 100 kilograms per hour of wet leather is 80% water. Thus, we have an input of 80 kilograms of air per hour and 20 kilograms of solids per hour. The dried leather contains 20% water, giving outputs of 5 kilograms of water per hour and 20 kilograms of solids per hour. Thus, the solids balance was indirectly accounted for in the problem statement. That is to say, the solids do not evaporate. They do not change the stream. They don't go into the air. The solids that come into the problem are going to have to be the solids that leave the problem. And because we know that there were 20 kilograms of solids that came into the problem, there also has to be 20 kilograms of solids that leave with the wet leather. Going on, the water removed is 80 minus 5, which is equal to 75 kilograms of water per hour, or 100 minus 25 is equal to 75 if we look at the total water plus the solids balance. This is water added to the air. Thus, in that diagram, the upward arrow from the leather to the air. Thus, the airflow must be sufficient to remove the water. That is to say, a water balance for the air. So what we basically understand from this point is that we know how much solids came to the system and left the system, 20 kilograms. We know how much water came in, 80 kilograms, and how much water left the system in the leather, 5 kilograms. The difference, the amount of water that went from the leather to the air, is 75 kilograms. So since we know the amount of water there, we can do a water balance for the air because we know how much water came in with the amount of air we're trying to solve and how much water went out with the amount of air that we're trying to solve and how much was added. So in the next equation, which is a water balance, you have the water in the air in plus the water added, 75 kilograms, is equal to the water in the air out. So there you see X, which is the amount that we're trying to solve, in kilograms of dry air per hour times 0.01 kilograms of water per kilograms of dry air. These quantities are given to you, plus 75 kilograms of water per hour, which is the amount that we solved coming out of the leather, equals X, the unknown amount of air, dry air, times 0.02 kilograms of water per kilogram of dry air. And we need to solve this equation for X. When solving these problems, you need to be very sure that you are carrying the units that you have. But in solving this equation for X, the amount of air that's coming into the system, we get the following equation that you see on the top of your page, solving for X. The first step is to move all of the quantities that are associated with X over to one side and then divide them through. And this is how you get the equation you see before you. X is equal to 75 kilograms of water per hour, which was the amount of water that came out of the leather, divided by 0.02, the amount of air, the amount of water associated with the air going out, minus 0.01, which is the amount of water associated with the air coming in, and then you have the kilograms of water per kilogram of dry air, which is the units for the 0.02 and the 0.01. When you go ahead and start to solve that and start to cancel out some of the units that are on the numerator and the denominator, you have 75 divided by 0.01 kilograms of dry air per hour, which is equal to 7,500 kilograms of dry air per hour, which is solve the equation that we have. Going back to the book, we have now completed all the calculation necessary for the answer. However, we can check the above result by performing a water balance for the entire system. Water enters the system with the entering air and wet leather. It exits with the dry leather and exiting air. Thus the balance is water in minus water out is equal to 0. And when you do all the calculations of basically what you see in terms of the water in, 100, the initial amount of leather, times 0.8, which is the amount of water per amount of leather, kilograms of water per kilograms of leather, plus 7,500, which is the kilograms of dry air per hour, times 0.01, which is the kilograms of water per kilogram of dry air, minus 25, which is the amount of leather or kilograms of leather per hour exiting, times 0.02, which is the amount of water per kilogram of drier leather, plus 7,500 kilograms of dry air per hour, which is the amount of air exiting, times 0.02, which is the kilograms of water per kilogram of dry air. So what you have in essence is the first, inside of the first parentheses is the amount of water in, water coming in from the leather, water coming in from the dry air initially, minus the second parentheses is the amount of water exiting with the dry leather, plus the amount of water that's exiting with the wetter air. And so you have your 85 plus 75, if you do the math, minus 5 plus 150. And then you get 155 minus 155 is equal to 0. Thus, the water mass is balanced. The reason why it comes out to be 0 is because the amount of water coming in minus the amount of water coming out, there is no accumulation that's inside of our system. Basically, what comes in will go out, and this is what was just proven. Next, we move on to the section on mass balance and mixing. In this example, a blend of sorghum syrup is to be produced by mixing pure syrup with corn syrup and a semi-syrup to produce 100 kilograms of blended product. Properties of the three syrups are shown below. All percentages are by mass. In the table below it, you see the different components of the syrups. There are three different kinds of syrups: sorghum syrup, corn syrup, and semi-syrup. And the three components that we're concerned with are water, sugar, and flavor. We want to come up with 100 kilograms of the desired blend for which we're given the particular components, and what we're trying to find, which is in the right hand column, is the kilograms of each of the different syrups that we're going to add to be able to get the desired blend with the types of components that are listed at the bottom. You will note that the percentages of all the components, because they're percentages, should add up to 100. So 24 plus 75 plus 1 will give you 100 percentage. Coincidentally, we're trying to make up 100 kilograms, and so that ends up being 24 kilograms of water, 75 kilograms of sugar, and 1 kilogram of flavor that's actually needed in the desired blend of the three different syrups. Alternately, this system can be shown by diagram example 2, which you should also be able to access in Blackboard. What this diagram shows is how all of the different components in the three syrups mix to produce the desired blend. You may wish to print this out while you go through this exercise. The solution is as follows from the book. 3 mass balances are needed: sugar, flavor, and total mass. Using the symbol following each syrup name in the table, we write the mass balances as follows. S will be your sorghum syrup, C will be your corn syrup, and P will be your semi-syrup. The total of all three in kilograms will be S plus C plus P is equal to 100. If you did a balance on the sugar, noting the percentages of sugar in each of the three syrups, you have 0.755 times the kilograms of sorghum syrup, or S, plus 0.8 times the kilograms of corn syrup, or C, plus 0.59 times the kilograms of your semi-syrup, or P, which is equal to 0.75 times 100, which comes out to be the percentage of sugar in the desired blend times the amount of desired blend that we want in kilograms. 0.75 as the percentage and 100 kilograms, which is the desired amount of the desired blend that we want, which comes out to be 75 kilograms. The flavor, by the same token, comes out to be 0.015 S kilograms of sorghum syrup plus 0 percentage of the corn syrup in kilograms plus 0.01 times the kilograms of the semi-syrup, which is equal to 0.01 times 100, which is the percentage that it's in the desired blend times the amount of the desired blend, which turns out to be equal to 1. Rearranging the flavor balance and solving for P in terms of S gives P is equal to 100 minus 1.5 S. If you look back at the flavor equation, you can see that the corn syrup, because there is no flavor in the corn syrup, falls out of the equation, and all you have left is your percentage it's in the sorghum, your percentage it has in the semi, and you have 1 on the other side, which is the amount that you eventually want. So from this equation, you see that once you rearrange it, you multiply it ultimately by 100, or you're dividing it by 0.01, pretty much the same thing. You end up with P is equal to 100 minus 1.5s. You can substitute this relationship for P in the total mass balance equation given S plus C plus 100 minus 1.5s is equal to 100, which means that you took the last equation and put it in the first equation at the top that has the word total next to it, the total mass balance equation. When you solve this, because you have S, which you move to one side, and the hundreds will actually cancel out, you have C is equal to 0.5s. So it says substituting for C and P in the sugar balance equation given, you take both of the two equations, the P equation after you rearrange the flavor balance, and the C is equal to 0.05s from solving the total mass balance equation. Putting that into the sugar balance equation, you will do the substitution that you see below, and you see 0.75s plus 0.8, which is C, what you substituted in, plus 0.59 times your P substitution is equal to 75, which is the amount of sugar that you want in the desired blend. When you solve all of this, you find that S is equal to 55.56, and then you can go back to the equations at the top to solve for C and solve for P. C comes out to be 1/2 of S, which you have from the total mass balance equation, which is 27.78, and then your P comes out to be 16.66. On the next page, you see that you can check the results of your equation by substituting the values that you got back into your total mass balance equation. You found that S was 55.56, that your C was 27.78, and then your P, the amount of semi-syrup, is 16.66. When you add these together, you get 100. Essentially, this combination of ingredients can be used to produce the desired blend. Some ingredient combinations could not be used. For example, if the corn syrup of the above problem contained a 1.1% flavor level, no combination of ingredients could reduce the flavor level to 1%. In general, if a solution of the mass balance equations results in a negative value for at least one ingredient, this indicates that the desired blend is not possible. Normally, you will not be given problems where it's not possible, but that isn't a possible outcome. This completes the third lecture of Topic 1 Problem Solving. If you have any questions, please feel free to contact me at the email address listed on the syllabus in Blackboard. Thank you.